Hello there folks. So today I'm going to talk to you about this. This is called NMR, Nuclear Magnetic Resonance Spectroscopy. Okay, Nuclear Magnetic Resonance Spectroscopy. Now what I'm going to do is I'm going to very quickly explain to you what this method is, kind of how it works. Okay, so here we go. So here on this plane here, right? So let me just explain to you. You see, when we have a charged particle, okay, a charged particle. So when the charged particle, right, when it spins, okay, let's say an electron, right, when it spins, what happens is it produces a magnetic field. Okay, it produces a magnetic field. That's what it does. So that is why in unit 1, when we did this, when you have two electrons, right, when you put them into an orbital, we always put one electron up, one electron down, because one electron is spinning clockwise and the other electron is spinning anti-clockwise. So what happens is the magnetism which is produced by one electron is cancelled out by the other electron. So in this method, which we call NMR, this method only works with odd number of nucleons. Okay, nucleons, which means that, like for example, like carbon 12 6, carbon 13 6. So you see, in this case this is odd, right? This one we can do, this one is even, we cannot do. Okay, so same thing goes with other elements, like for example, let's say hydrogen. This one can work. Another isotope of hydrogen, which is called deuterium, cannot. Okay, it must be an odd number, like fluorine 19 can. Okay, fluorine 19 can, but if there's such thing as fluorine 20, which there is, this one cannot. So the moral story here is the nucleon number must be odd. Okay, the nucleon number must be odd. So that's the criteria. So in this method that we'll be looking at, we're only looking at two things. We're looking at carbon 13 NMR and we're looking at proton NMR. So proton NMR is basically proton hydrogen. Since the good thing is all elements have hydrogen 1, which is much better, but not everybody has carbon 13, so sometimes we have to infuse it, but that's how it works. So we don't care, we don't have to worry too much about the details. So how does this method work? So to make things simple, what we do is we have a sample. Okay, so we take a tube, we take a long tube, and in this tube we put our sample. Okay, so we put our sample in the tube. Okay, so that's sample. And then what we also add another chemical, and this chemical is called TMS. I'll tell you later what TMS is for. Okay, then what we do is, in this method, we spin this tube really fast. Okay, we spin it really fast. So what will happen is the protons, okay, so protons are also charged particles, you see. So the protons start spinning and they produce, the protons start spinning and they start producing a magnetic field. Okay, so there's a magnetic field. So a magnetic field is produced. While this is happening, this entire thing is kept in a very strong electromagnet, let's say north and south. So it's kept in a very strong electromagnet. So when the electromagnet is turned on, the flux goes usually from north to south. Okay, so now suddenly you have protons which are producing magnetic field, which is now placed in an external magnetic field. So like magnet versus magnet, okay, something like that. So what will happen is, if you imagine what is happening currently is something like this. Let's say if we could look into this, right? Let's say if this was a proton, the north pole of the proton and the south pole can arrange itself in this way. That means south, north. That means it can follow the flux, you see, like north to south, or it can go against the flux, like south to north. You see, like up here, right, it's going from north to south. Perfect. So like this magnet, this proton is north to south. Perfect. Follows the arrangement. But there are some protons which will be aligned wrongly. That means it will be going against the magnet. Well, it doesn't matter at this moment, whatever it is. So during this point, when this all is happening, what we do is we send in radio frequency. Okay, radio frequency. All right, so we send in radio frequency. So when we send radio frequency, right, what will happen is these magnets I told you just now, these things will start flipping, they will start flipping back and forth. They will start flipping. When they flip, they start producing a frequency outwards. Oopsie. They start producing a frequency outwards. Okay? They start producing a frequency outwards. So this frequency that's coming out from this tube, okay, this frequency that is coming out from the tube, this is the frequency that we are trying to detect. So we detect this frequency. That is what we're doing. Now, whatever I just told you for the last few minutes is actually not really important to you. You don't need to know how this instrument works and so on. But you need to know that when the sample is placed in a magnetic field and radio frequencies are passed into the sample starts producing some signals or some frequencies. And these are the frequencies which are measured. Okay? These are the frequencies that are measured. So this is the basis of NMR. All right. So what we're going to do is we're going to look at some samples. How can we use this method to detect the shape of a molecule? All right. So when we do this, right, one very important concept that we need to understand is called symmetry. Okay, symmetry. So this is important. So let's talk about this. So symmetry is a very important concept here. Like, for example, let's say if we look at this molecule here, right? Let's say this is propane. So this molecule is called propane. So currently, I want to explain both of this. So let's say all of these carbons are carbon 13 lah. Okay, let's say this carbon 13. All right. If you look at this molecule, right, what we can do is we can actually split this molecule in the center here, and you will get two sides which look identical to each other. Now I want you to imagine another thing, right? All of these carbons are like ball, okay, like a football, okay, and all the hydrogens are like footballs. So then maybe that will be easier for you to understand. Okay, so like imagine this is a ball and we cut the ball right in the middle. So we'll get two pieces which are equal, right? So we'll get this side which is equal to this side, right? So what I want you to understand is this. I want you to understand that this carbon and this carbon are exactly the same. They are actually identical to mirror images of each other, right? And I also want you to understand that this proton, and this proton, and this proton, and this proton, and this proton are identical to each other. They are mirror images of each other. On the other hand, this proton and this proton are identical to each other, but they're not the same as the others. And this carbon is different. Okay, so currently what we have is we have two hydrogen environments. Okay, two hydrogen environments. So hydrogen environments. Okay, we have two. So in this case, it was the A and the B. And then we also have two carbon environments. We have two carbon environments, and those are the A's and the capital B's. So we have two sets of environments. So what does this mean? Why is this important? Okay, I'll explain this in the next video.